Hello my dear student. So today we'll be talking about linear system and a matrix representation. So let us talk about two system, say dx1 by dt. This is equal to general equation a x1 plus a b x2. This is the first equation, and then the second equation is dx2 by dt, and this is equal to say cx plus this is small c, this small c, dx2, here it is x1. So this is a linear system because the degree here is 1, here also it is degree 1, here is also degree 1, here also degree 1. Okay, so it is obvious that 0 0 is a fixed point of this system. So this system can be represented by in matrix form dx by dt. This is equal to ax. So here capital A is given by capital A is given by the matrix. Capital A is equal to is the square matrix A, B, C, D, and capital X is equal to column matrix x1, x2. By simple matrix multiplication, so this system of equation can be written in this matrix form. This system of equation can be written in this matrix form, where the matrix A is given by this. Okay, so and the column vector x is given by this one. So given system of equation, linear system of two equation can be represented by this matrix form. Okay, so the characteristics of the fixed point, the nature of the fixed point, the behavior of the fixed point will be determined by the characteristics root of this square matrix or the eigenvalues of this square matrix. That is all about today's lecture. Okay, so what we do normally, how to let us solve this one. First, as I told you, this system of equation now can be converted into a single second order differential equation. What to do? Then first you differentiate this equation with respect to t. Then what you get? You get d square x1 by this is dt. This is equal to a dx1 by dt plus b dx2 by dt. So this we want to eliminate one variable. Let us eliminate x2 variable. So we don't want this dx2 by dt. So then you can substitute this value from here. So what you get, this is a dx1 by dt, then this is plus b, and this one is how much? This one is this is small c x1 plus dx2. So this you get again here x2 is involved here, x2 is involved, but from the first equation you can eliminate x2 in terms, or you can convert x2 in terms of x1 and its derivative. Okay, if you transfer this side, bx2 is like that. Okay, so this is equal to then how much? This is equal to, you can write this like this, a dx1 by dt, this is plus bcx1 plus this is Now let us write D first, then B, D first, then bx2. So what is bx2? Bx2 is given by this one. Bx2 is equal to dx1 by dt minus ax1. So ultimately what you get? This implies that d square x1 by dt, okay, dt2, dt2 here. So this is equal to how much? This is equal to a dx1 by dt here. All right, yeah, then here plus b cx1, and then plus d is here. Then what is b? bx2 is equal to dx1 by dt, okay, so minus ax1. So this, you get it. All right, so then so this implies that what? Then you can write like this, simplify like this, d2 x1 by dt. So this is equal to how much? This is minus of a plus d dx1 by dt, and this, how about this one? This is plus x1 common, so that will be what? This is d, this is a, this is d, so this will be a ad minus bc. This is equal to x1, this is equal to 0. So this is the second order equation in x1 variable. Okay, so similarly you can eliminate, you can write down second order equation, the x2 variable. So the same thing will be there. You can do it yourself. What will you get? You will get d2 x2 dt to here. Okay, so here it is to here, and then minus a plus d, it will be here, then dx2 by dt, then plus ad minus bc into x2. You will get this one, the same equation. Okay, so what is a plus d? A plus d, this is the a plus d, sum of the diagonal. That is, we call trace of the matrix A. Okay, trace of the square matrix A is a plus d. So what is ad minus bc? So ad minus bc is the determinant of the matrix A. So this is what? This is trace of matrix, given square matrix, and this is what? This is the determinant of the given square matrix. All right, so again, if you find out the characteristic equation of this one, so how to solve this one? You know how to solve this one, you already know it. You put here m square minus a plus d m plus ad minus bc. You get an equation, solve that equation for m, and then you get a solution. Okay, you get a solution in terms of exponential function. You get a solution in terms of exponential function. Okay, so that is normally how we solve such type of differential equation. All right, so again, what I tell you is that if you find out the characteristic equation of this one, if you find out the characteristic equation, so what is the characteristic equation of this one? You can do it. The characteristic equation is lambda square minus a plus d lambda plus ad minus bc. So this is the characteristic equation. So you have same equation. The characteristic equation is equal to the auxiliary equation. The characteristic equation is equal to the auxiliary equation. So you will get the root of the equation m square minus a plus dm plus ad minus bc is equal to 0 is exactly equal to root of this characteristic equation. Okay, so the characteristics root of the given matrix, the matrix form play a vital role for the nature of the fixed point. Okay, so let us see what is the solution of this equation. Let us see what is the equation of this solution. First, let me go to the second window. Yeah, if lambda 1 and lambda 2 are the roots of this characteristic equation, if lambda 1 and lambda 2 are the roots of the characteristic equation, then what do you get? X1 is equal to how much? Then x1 is equal to, say, constant a, e to the power lambda 1 t plus constant b e to the power lambda 2 t. So this is the way we find out the solution of the given differential equation. Okay, so this for this differential equation, for the first differential equation, if the characteristics roots are lambda 1 and lambda 2, yeah, if the characteristic root are lambda 1 and lambda 2, then capital A e to the power lambda 1 plus capital B e to the power lambda 2, where capital A and B are constant according to the initial condition, that is the solution. Again, this equation and this equation, their characteristic equation are same. Okay, therefore the characteristic root are same, so the solution will be exactly similar except the constant. So then how we write a solution? How you write a solution you can write for the second equation, x2 is equal to, so instead of a here it will be capital C is here, e to the power, since the equation same characteristic equation, characteristic root are same, lambda 1 t plus b e to the power lambda 2 t. You can write like this. Okay, so this is the first equation, x1 solution, this is x2 solution. So this you can write in the matrix form again. Okay, this, suppose you can column matrix, this can write in the column matrix capital X, that is x1, x2 is your capital X, this is your capital X. All right, so this is equal to how much you can write? You can write a, b, sorry, this should be d, this is d, capital D, this is capital D. Okay, so a, b, c, d, here you can write like this. Okay, then here e to the power lambda 1 t, e to the power lambda 2 t here. So this is a column matrix, right? So you can this solution you can write in the matrix form like this. Okay, in the matrix form like this. Again, if you put this a, c, this is column matrix, let us put this column matrix as u1. Okay, then you can write like this, then u1, u2. So this is this is u2, this is u1, column matrix. Then you can write like this. Okay, then you can write e to the power lambda 1 t, then here e to the power lambda 2 t here. All right, so you can write like this. Then you can, so this is now is vector. Okay, here it is constant, this is constant a, this is constant b, and constant d, constant c. But if you write a column AC, then it is going to be a vector, and u2 is also a vector now. So then how you can write this is, you can write like this, u1 e to the power lambda 1 t plus u2 e to the power lambda 2 t. So the given system of differential equation now has solution, has solution like this. Capital X is a vector, this x1 x2 column vector. This is equal to u1, it is a column vector, AC e to power lambda 1 t. So e to power lambda 1 t is, it is a number, but this is a vector. Okay, so plus u2 e to power lambda 2 t. So this is the solution. Okay, for a given system of differential equation, this is solution in matrix form, in vector form. Right, so it is a solution in the vector form. So we want to know what is u1 and u2. Okay, what is u1 and u2? You already knew that lambda 1 and lambda 2 are the eigenvalues of the square matrix A, B, C, D, where A, B, C, D are small letters. Okay, capital A, B, C, D, they are constant, we have defined. So we want to know what is this vector column vector, what is this column vector. So let us see this is a solution. So since this is a solution, it should satisfy the given differential equation. Now what is the given differential equation? The given differential equation in the matrix form is dx capital, this is the sorry again start this problem. Yeah, now it will be okay. So the given differential equation is dx by dt, this is equal to ax. In matrix form, the given differential equation is this one. So since this being a solution, this solution satisfy this equation. So now let us find out what is this u1 u2 vectors. We know that lambda 1 lambda 2 are the eigenvalues of the matrix A. So this is a solution. Let us differentiate it. Then what do you get? If you differentiate x is equal to, if you differentiate x, this is equal to u1 e to power lambda 1 t plus u2 e to power lambda 2 t. What do you get? Let us differentiate it. So that means what? Dx by dt, this is equal to, if you did, this is a constant vector, so if you differentiate it, now what do you get? You get lambda 1. So lambda 1 u1 e to power lambda 1 t plus, similarly here what do you get? Lambda 2 u2 e to power lambda 2 t. So this is what you get. So what about the ax? What about the ax? Ax. So this is equal to how much? This is equal to x. You can write x in terms of u1 u2. This is the matrix, and here it is multiplied by the column vector e to power lambda 1 t e to power lambda 2 t. So this is ax. This x you can write in this form. Okay, I have already shown you x you can write in this form. So then what is this multiplication? This is, you can write a u1 a u2. This is the matrix multiplication, a this one, and then e to power lambda 1 t e to power lambda 2 t. So since x is a solution of the given differential equation, dx by dt must be equal to ax. All right, that means this expression must be equal to how much? Must be equal to this much. So this is equal to how much? This is equal to u1 u2, this is e to power lambda 1 t e to power lambda 2 t. You can write like this. Okay, so ultimately what, since x is a solution, this must be equal to this one. This quantity must be equal to this quantity. But this quantity, how can you can write this? You can write like this. this is lambda 1 u1 lambda 2 u2, this is the matrix. All right, so into e to the power lambda 1 t e to the power lambda 2 t, you can write like this. Okay, so ultimately this quantity equal to this quantity means that this quantity is exactly equal to this quantity. Okay, so this is a column matrix, this is also column matrix. That means, you know, they are exactly same. That means what? This is, since it is a, you know, this one, yeah, this since this one is exactly equal to, what you get ultimately, what you get after multiplication, what you get. So this is equal to, you will get a u1 is equal to lambda 1 u1 and a u2 is equal to lambda 2 u2. You will get this one, equality of these two, you know, equality of these two will give you these two equation. Okay, these two equation, what does it say? It says that u1 is the eigenvector corresponding to the eigenvalue lambda 1. Okay, similarly, what it say? It says that u2 is the eigenvector corresponding to this, you know, eigenvalue. So that is what I want to tell you. That is exactly what I want to, how to solve the given differential equation in matrix form. So if you know the eigenvector and the eigenvalue, you will get the solution. That is as simple as it is. Okay, so if you know the eigenvalue and eigenvector, if suppose eigenvalue is lambda 1 and corresponding to this eigenvalue u1 is an eigenvector, so then this quantity plus corresponding to the eigenvalue lambda 2 u2 is an eigenvector, then this quantity plus sum of these two will give you the general solution of the given differential equation. Okay, sum of these two will give you the general differential equation. Okay, so solution of the given, general solution of the given differential equation. Okay, so that is, you know, that is the what I want to tell you. What is u1 and u2? They are eigenvector corresponding to the eigenvalue lambda 1 and lambda 2. All right, so such type of system we call it coupled, you know, such type of system you can write it properly what I am telling you here. Okay, so proper note you can write down. So such type of differential equation, say dx1 by dt is equal to ax1 plus bx2, you know, dx2 by dt, this is equal to cx1 plus dx2. So this is coupled, means, you know, the two variables are involved in the first equation. Okay, so here x1 is also here, x2 is also here, here also, you know, x1 is also here, x2 is also. So this is called coupled, you know, coupled differential equation. Okay, this is the coupled because both the variables are involved, pairwise involved, coupled, you know, coupled. Okay, so we want to decouple it. Decouple means what? Decouple. Okay, decoupled by using some transformation. If somehow if you are able to eliminate this one, then dx1 by dt is equal to ax1. It is very straightforward to solve that equation, very easy. Okay, so similarly by some, you know, transformation, if you are able to eliminate this second variable, only dx2 is here, then it is very easy also to solve such equation, very simple and easy. So that, you know, from the given differential equation, somehow using some transformation we want to decouple it, means from the first equation you want to eliminate the second variable, from the second equation you want to eliminate the first variable, then you get a simple equation. That simple equation you can solve it easily, but their dynamical behavior are same. Okay, suppose the fixed point is attractive and the new system is also, in the new system the fixed points are, you know, attractive. Okay, if the fixed point is repulsive, then the new system, that means the new decoupled system, is also in the fixed point is also repulsive. So dynamical behavior, what we want to know, we want to know the dynamical behavior, okay, of the system. All right, so that means the two systems are qualitatively equivalent or similar, okay. Then there is no harm studying the simpler dynamical system. You will get the behavior of the complex dynamical system, okay. So that is the main task. All right, so now how to decouple it, how to simplify it, how to simplify it. Jordan canonical form of the matrix, it is all about the matrix, the property of the matrix, okay. So somehow we can reduce the given matrix into a simpler matrix or Jordan canonical form. Let us see how it works. Let us see how to decouple it, and then let us find out the transformation so that the given differential equation is decoupled, okay. The given differential equation is decoupled. So for that, what we have is dx by dt is equal to ax. So here it is coupled, we want to make it decoupled, okay. So then you put p, p is equal to this matrix u1 u2. We have already defined what is u1 u2. All right, so you put p is equal to u1 u2, okay. So by Jordan canonical transformation, what you get, so p inverse, p will be invertible, okay, because u1 is the eigenvector corresponding to the distinct eigenvalues lambda 1, and u2 is the eigenvector corresponding to the eigenvalue lambda 2, and lambda 1 and lambda 2 are distinct. So therefore u1 and u2 are linearly independent vector, therefore p is invertible. So p inverse a, p inverse a, p is equal to, you can write it in terms of diagonal matrix. The diagonal matrix will be, what are the entry in the diagonal matrix? Very interestingly, these are the eigenvalues 0 lambda 1. All right, so this is already how to make it in the Jordan canonical form. In this one, this is lambda 2, suppose this is d. All right, so then using this matrix p, so this matrix A can be reduced in the diagonal form, the simple diagonal form lambda 1 lambda 2. All right, so let us see now then how does this work. Let us see. You can easily deduce it, okay. Next time I will explain, you can do it yourself also, how it comes. We have already studied in the unit 1 also, I think. So and then let us see. You put x is equal to py, then what happen? You put x is equal to py, capital Y. So what is x? X is the column vector x1 x2. What is y? Y is column vector y1 y2, okay. And what is p? P is given by this square matrix. u1 is the eigenvalue, eigenvector, u2 is another eigenvector. They are linearly independent, okay. Then you define the diagonal matrix D like this, okay. So using this matrix, let us transform x into py like this, okay. Py is equal to x. Py is equal to x. Then what is dx by dt? From this, what you get? Dx by dt is equal to how much? This is equal to p dy by dt. All right, so p dx by dt is equal to p dy by dt. So this, you get it, okay. So then Then what is dx by dt? Dx by dt satisfy the given differential equation a x. Dx by dt is equal to x. This is equal to p dy by, this is capital Y, okay, this is capital Y, dy by dt. So this dx by dt is equal to ax. So this implies that what happened? This implies that, you know, so since p is invertible, multiplying both sides by p inverse, what you get? P inverse a, you know, p inverse ax is equal to how much? This is equal to dy by dt. All right, p inverse. So okay, and then what is, you know, x is equal to py. So then ultimately what you get from here? If you put x is equal to py, what you get? Dy by dt is equal to, so here you put here you put x is equal to how much? X is equal to py. So then what you get? It is p inverse a py, but py is diagonal matrix D, na? So that means what? Dy by your dt is equal to how much? Dy by dt is equal to dy. So that means what? That means what? This is dy by dt, this is diagonal matrix, this is equal to diagonal lambda 1 0 lambda 2 0, sorry, so I have to use eraser here, okay. So anyway, you know, I just let me override here. This is 0 and here it is lambda 2, and y capital Y means you know, y1 y2 here. All right, so then in simple form, how can you can write this one? This now you can write, you know, let me just open another window. I don't want to erase. Let me come back after some time. Then what happened? So this is you know, d by dt of y1 y2 is equal to how much? Lambda 1 0 0 lambda 2 y1 y2. So from here, you know, what you get? Dy 1 by dt this is equal to how much? This is exactly lambda 1 y1, okay. And from the second one, what you get? Dy 2 by dt is equal to how much? This is lambda 2 y2. So what you have from the given differential system of differential equation, dx1 by dt, this is equal to a x1 plus b x2, and another one dx2 by dt, this is equal to, you know, cx plus d x2 x1 here. This is called coupled because two variables are here. This is, we call it coupled differential equation, linear differential equation, okay. So by using the transformation, you know, by using p is equal to, you know, u1 u2, where u1 u2 are again vectors, okay. And then what we use the transformation, x is equal to, you know, x is equal to py. Then, you know, p inverse a p is equal to diagonal matrix D. So using this, you know, using this transformation, so this decoupled, you know, this coupled differential equation now reduced to this simple one, okay, reduced to this simple one. So this you can easily solve it. What is the solution? Lambda 1 is equal to, you know, some constant e to the power lambda 1 t exponential function, this one also. So it is very simple to solve this equation. The only thing is that, you know, the dynamical, we are studying dynamical behavior of the fixed point, or the, we are studying the dynamics. All right. So the dynamical behavior of this equation is exactly equal to dynamical behavior of this, equation. The only thing is that this is a very complicated system of differential equation, but this one is very simple. All right. This one is very simple, this one is a little bit complicated. So since the dynamical behavior of this given equation is exactly similar to this one, then it is better to study this one, because it is easier. So from this given equation, you can transform to the decoupled system like this. You can solve it easily, and you will understand the dynamical behavior of the fixed point. Okay. So all right, so fixed point are same. The fixed point is here, it is also 0 0 is the fixed point. Here this is 0 0 is also the fixed points. Fixed point are same. The nature of the fixed point, they are same. The dynamical behavior of the two systems are exactly similar. Okay. So this is the theory I want to tell you today. Okay. I think you can listen it again and again, and then you can write down the proper note from this one, and this is a very fundamental one. Okay. So this much I want